Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning in to this video in which we'll go through eigenspaces. So the eigenspace of a particular eigenvalue lambda is the zero vector together with the set of all eigenvectors associated with that eigenvalue. So what we saw last time is we have an n by n matrix A. It will have up to n eigenvalues, and each different eigenvalue has a different eigenvector. But remember, if x is an eigenvector of A associated with lambda, any scalar multiple of it will also be an eigenvector with the same eigenvalue. So all of those eigenvectors together with the zero vector make up the eigenspace of an eigenvalue lambda. But what we're going to do is look at cases where an eigenvalue is repeated. So that means its algebraic multiplicity is more than 1. That means it's either a double root or a triple root or whatever of the characteristic polynomial. Now, when this happens, when lambda is a repeated root of the characteristic polynomials, sometimes it will have eigenvectors associated with it that are linearly independent, and sometimes they'll be linearly dependent. If the eigenvalues associated with a repeated eigenvalue turn out to be linearly dependent, we say that the matrix is defective, and that's what we're going to look at here. So defective matrices are important. We're going to look at this later on in this series, but it turns out that they can't be diagonalized. So let's go ahead and look at two examples that will hopefully make clear these concepts of algebraic multiplicity, geometric multiplicity, and a defective matrix. Let's look at these two easy examples and what their eigenvalues look like. So for A, if I want to find its eigenvalues, I find the matrix A minus lambda I. Remember, of course, I just subtract lambda from each of the elements on the leading diagonal, and the other elements I leave alone. So if I want to find the eigenvalues of A, I need to find the values of lambda that make this matrix in blue have determinant 0. So remember, its determinant is A, D, minus B, C. So this is the determinant of the matrix in blue. So if that equals 0, there is only one solution. If the first bracket here equals 0, lambda equals 1. But if the second bracket equals 0, lambda also equals 1. So because 1 makes the first bracket equal 0 and also makes the second bracket equal 0, we say lambda is a repeated root of this polynomial. Lambda equals 1 is a double root, and so its algebraic multiplicity of lambda equals 1, that's equal to 2. So lambda equals 1 has algebraic multiplicity 2. Now a similar thing happens in the second matrix. So it turns out that that 1 in the second matrix doesn't really change much. So the determinant of this matrix here is 2 minus lambda times 2 minus lambda, AD minus BC, but BC is again 0. So if the determinant equals 0, lambda equals 2, that makes the first bracket equal 0, and it equals 2 to make the second bracket equal 0. So lambda equals 2 is a repeated root for the second matrix, so again, it has algebraic multiplicity of 2. So the algebraic multiplicity of eigenvalue lambda equals 2 is 2 because it is a double root of the characteristic polynomial. So let's go ahead now and find the eigenvectors for each of these matrices. So A minus 1i, so A minus I, turns out to be the 0 matrix, right? So I want to solve when that equals 0. But if I have the 0 matrix times any vector, it will always give me the 0 vector. So actually, every single vector in R2 is in the null space of this matrix, the 0 matrix, and that means every single vector will be an eigenvector of this matrix here, which was the identity matrix. So A and B can be anything we like. So we actually have two free variables. So I'm going to write it like this. We have A, 1, 0, plus B, 0, 1. That is the set of all solutions to this. A and B can be whatever we like. So if you put in any value for A and any value for B, and you do this sum here, down the bottom, then it will be a solution to this equation here, and hence an eigenvector of the original matrix. So we have, these are the eigenvectors, 1, 0, and 0, 1. They are eigenvectors. Any scalar multiple of them will also be an eigenvector. Now let's look at B, what its eigenvectors will be. So if I take B minus 2i, I'm left with something that's almost the 0 matrix, but it still has that 1 up in the top right-hand corner, and that will change everything. So if I want this matrix B minus 2i, I want to times it by a vector, I'll call this CD, to get the 0 vector, right? I could make this an augmented matrix, and it's already in row reduced form. So what I have here is that D must equal 0. There's no other number it could be. So in the previous example, A or B were both free variables. Here, D is not a free variable. It must equal 0. But C can be equal to anything we like, because 0 times C equals 0, infinitely many solutions. So that means the eigenvectors here are of the form C times 1, 0. So any number times 1, 0 will be an eigenvector of this matrix here. So we say that the eigenvector is just 1, 0, and any scalar multiple of it will be an eigenvector. So look at the eigenvalues in both cases. They both had an algebraic multiplicity of 2 because they were a double root of the characteristic equation. But look at A. It has two vectors here that are linearly independent. We know that because neither is a scalar multiple of the other. So, because there are two linearly independent eigenvectors associated with this eigenvalue, the geometric multiplicity of lambda equals 1 is also 2, because there are two linearly independent vectors. But if we look at B, you'll see there's only one linearly independent eigenvector associated with the eigenvalue. So here, the algebraic multiplicity was 2, but the geometric multiplicity of this eigenvalue is 1. So what that means is that B is a defective matrix because the geometric multiplicity is less than its algebraic multiplicity. So the idea here behind a defective matrix is when we have an n by n square matrix, we can also have a case where that n by n matrix has n linearly independent eigenvectors. But when we have fewer than n linearly independent eigenvectors, we say the matrix is defective. So this means that the dimension of the eigenspace of lambda, which is the number of linearly independent vectors in the eigenspace, that's less than the algebraic multiplicity of the eigenvalue. So in other words, the eigenvalues in the eigenspace don't span the maximum possible dimension. They span less than the maximum possible dimension. So the eigenspace here is just the set spanned by these two vectors here, right? The 0 vector is already in this span. We just had to say on the previous slide that the eigenspace is the union of the zero vector, because remember we decided that the way we defined it was that the zero vector is not an eigenvector. Okay, so here the eigenspace of this eigenvalue, lambda equals 2, is only one dimensional because it only has one linearly independent vector. So all eigenvectors will lie on the line that goes through 0, 0, and 0, 1. All those vectors span a straight line which is one dimensional. Whereas here, those two vectors, because they are linearly independent and they have two entries, they span the entirety of R2. So that means that any vector in R2 will be an eigenvector of this matrix here. So its eigenspace is the maximum possible dimension. So there is a different eigenspace for each eigenvalue, and sometimes you may have a repeated eigenvalue, but you'll also have other eigenvalues as well. All right, this has been the luckiest maths teacher in the world. Have a great day.